Today we're going to be talking specifically about water and about its structure and about some of the specific properties that it has that make it absolutely crucial for life. Let's look at the structure of water first. You already know that the formula for water is H2O, and so what that looks like is that you have an oxygen and you have two hydrogens bonded to it, and oxygen also has some extra electrons in its outer shell that are up here that aren't bonded to anything. And so as a result, these electrons kind of shove those hydrogen bonds down a little bit further so that the water molecule takes on a bent shape. Again, that's not something that I expect you to understand why that happens. We'll talk about it a whole lot more in chemistry next year. But these lines here are representing shared electrons between the oxygen and the hydrogen. Now, just like kids don't always share their toys very nicely, sometimes atoms don't share their electrons very nicely either. And in this particular case, oxygen is kind of a bully. And oxygen is going to hog the electrons a whole lot more of the time than it's going to allow hydrogen to have the electrons. They get to share them so that everybody gets to have 8 electrons in their outer shell, or at least for hydrogen they only need 2, so that they can have their outer shell full at least part of the time. But because oxygen's a bully, it's going to keep those electrons more of the time because it's bigger and it's stronger. And so as a result, because it's keeping the electrons toward itself more of the time, it takes on a partially negative charge. And we talk about that partially negative charge by using the Greek letter delta and then a negative sign to show that it's not a whole negative charge. It's not a -1, but it is a partial negative charge. The hydrogen, then, because it's deprived of some of those electrons part of the time, its charge isn't completely balanced either. And so these guys have a partially positive charge on that end. And as a result, water is called a polar molecule because it does not share its electrons equally. And because it doesn't share them equally, it then has one side of the molecule that's got a partial negative side, and then the other side of the molecule is a partially positive side. Okay, so why is that important? Well, it's important for a couple of different reasons. One reason is because it makes water able to dissolve things much more easily. You have long noticed that water will dissolve things. You can take sugar or salt and stir it up in water, and it looks like the sugar or salt disappears, but you can taste it and you know that the sugar or salt is still there because you can taste salty water, you can taste sugar water. If you go to the ocean and you happen to get water in your mouth, you know it has salt in it because you can taste it. If you get the water on your skin and then the water evaporates, sometimes you've got a layer of salt left on your skin if you've been swimming in the ocean. So just some terms here that you need to be aware of. If you put something in water to dissolve it, water is called the solvent. And let's say that I put salt in the water, and that's what I'm going to try to dissolve. Salt is called the solute. And anytime that I have a situation where water is my solvent, that's going to be called an aqueous solution. So the result of dissolving something in something else, whether it's water or not, it's a solution. I can have a solution of all kinds of things. I can dissolve gases in water. I can dissolve solids in water. I can even dissolve gases and other gases, and all of those would be solutions. But if I have a solution where water is my solvent, then it's going to be called an aqueous solution. So why is it that water is so good at dissolving things? Well, if you remember yesterday, we talked about salt, and we said sodium has given up one of its electrons to the chlorine, so it has a positive charge, and that's not a partial positive, that's a whole positive charge because it's given up an entire electron. Chlorine, because it's gained this electron from the sodium, it has a negative charge on it, and it's a whole negative. It's a -1 because it's gained an entire electron. So what happens is that when you take this salt and you put it in water, the salt is all in chunks like this. Whoops, got carried away there. Okay, so it's going to look like this in this block where all of these positive and negative ions are attracted to each other. But you put it into water and the water starts moving around and banging into it. And what happens then is that around this positive side, the partial negative side of the water is attracted to the positive ion in the sodium. And so the water molecules start to surround these ions like this. And when they start surrounding them and then carrying them away from the big chunk of salt, then the salt is dissolved in the water. Now with the chlorine, the water molecule is going to turn itself and it's going to orient itself the other way because the hydrogen is the part that's positive. And like we said, opposites attract. So the partial positive side with the water molecule with the hydrogen is going to be attracted to this negative chlorine. So with these guys, the water molecules are oriented the opposite direction as they were with the sodium. So that is what makes one of the properties of water the fact that it will dissolve so many different things. And water is actually called a universal solvent. It doesn't dissolve everything, but it dissolves a lot of things. Why is that important? Well, because water dissolves so many things. Let's take trees, for example. We know that the leaves have to have water to run photosynthesis. Well, where's the water? The water's down in the ground. And so the root system and all the other systems in the plant have to carry that water from the roots up to the leaves. And when they do that, they're also carrying other nutrients that the tree needs as well. And then once the tree goes through photosynthesis and the leaves have made all this sugar, then the water can turn around and carry that sugar back down the tree to the roots where it can store things. The sugar dissolves in the water and enables it to carry it throughout the body. That's the same way with your body too. All of the food that you eat, all of the nutrients are going to get dissolved because a huge percentage of your body is made up of water. And so all of the nutrients get dissolved in water, and then the water circulates throughout your body via your blood, and then it carries all those nutrients to all the different cells that need it. So the fact that water can dissolve all of these things enables it to carry nutrients to all of the parts of plants and animals and other creatures that will need those nutrients. Okay, now like I said, water doesn't dissolve everything. You know that if you have a vinegar and oil salad dressing, for example, that the vinegar sinks to the bottom where the oil floats to the top. Well, vinegar is water-based. And so if you put oil and water together, they don't dissolve, they separate, but water does dissolve an awful lot of things, okay? The other characteristic of water that makes it have a lot of special characteristics that we see in life is the fact that it hydrogen bonds. And let me show you what that means. I'm going to get rid of this picture. And it still has to do with the fact that water is a polar molecule. And so the fact that my water molecule looks like this, again, the hydrogen's partially positive, the oxygen's partially negative. And so the partially negative down here is attracted to the partially positive on another water molecule. So there's a really weak bond that will form between this hydrogen and this negatively charged oxygen over here. And so this oxygen here will be very weakly attracted to the hydrogen on this one. And it will be attracted to the hydrogen on this one. And this one will be attracted to an oxygen on this one. So you can see what happens here is that, I forgot my other hydrogen. You can see what happens here is that all of these water molecules have this weak hydrogen bonding and this weak attraction to each other. This bond is not as strong as the bonds within the water molecule itself, but they are still a relatively strong bond. And you're going to hear the term hydrogen bonding a lot as we get in further in this chapter. So if you've ever noticed that when you take a glass of water, and I'm sure some of you've probably done this, if you have a glass of water and you fill it just as full as you can possibly fill it, have you noticed that you can actually get that water to arc up over the top of the glass? It's not level, it actually will arc up. Well, the reason that that will do that is because of the hydrogen bonding. It enables those water molecules to cling together and to have that water arc up that way. Anytime you see water droplets on anything, it's a result of hydrogen bonding. If you have ever noticed that if you are measuring something in a measuring cup, you may notice that at the edge, and I'm exaggerating it just so you can see it, but at the edge of the cup, that water tends to cling to it, and so it almost looks like the surface of the water is curved. And it is, because this is clinging, the water is clinging to the glass in just the same way that the water clings to each other. So both of those properties are called, it's called cohesion if the water molecules are bonding to themselves, and it's called adhesion if the water molecules are bonding to something else. And so again, this is what makes it possible for water to travel up and down trees, which seems to be against gravity. I mean, it's not like they've got gears and motors inside of a tree that's going to be able to make that water climb up to the top of a tree that's, you know, hundreds of feet tall. So instead, what happens is that it's the property of this water that it's going to cling to each other, and it's going to cling to the tubes that are inside of the tree that allow the water to travel, and then the water just kind of moves as a unit up these tubes that are inside the tree for transport. And when we talk about plants later in the year, we'll talk about a lot of how that mechanism works. But for right now, what you can understand is that it's a property of the water that makes that possible. Have you ever seen an insect sit on top of water? That's because of surface tension on the top of the water. And again, that surface tension has to do with the fact of the cohesiveness of the water molecules. The water molecules cling together with hydrogen bonding, and they almost make like a thin skin on top of the water, and the insects then are actually able to walk on top of that thin skin and stay on top of the water. Another special property of water is that it has a very high heat capacity. And the best way I can explain this to you is if you think about going to the swimming pool in the summertime, you know that on a really, really hot day, the sidewalk around the outside of the pool is hot to your bare feet because the sun's been shining on it. But if you get into the water's cool. Well, the sun's been shining on the water and the sidewalk equally, so how come they're both not hot? Well, the reason is because that water has a high heat capacity, and what that means is that it takes a lot of heat energy to make the temperature of the water actually rise. That's why if you get land that is around a large body of water, it doesn't get as cold in the wintertime because it takes so long for that body of water to cool down that the area around it tends to stay warmer in the wintertime as well. When you sweat, you put, your body releases water and puts it out on your skin, and then when it evaporates, that helps to cool you off, and that's all part of the high heat capacity of water. It has to take energy away from your body to make that water evaporate. Finally, the last special property of water has to do with the density of water. And again, this is related to hydrogen bonding because when the water molecules are in the liquid form, they're actually, the way they are structured, it makes it possible that the density of water is actually greater than the density of ice. And so that is really very highly unusual. If you have melted butter and solid butter, you would notice that the solid butter is going to sink to the bottom. So for almost everything, most of your solids are going to be more dense than your liquids. But the way God has created things, it's exactly the opposite of that for water. And so ice, if you have a glass of water and you drop an ice cube in it, what happens to the ice? Well, it floats. And it floats because it is less dense. And that is really, really important for all of our aquatic creatures who live in cold waters, because then the ice will float on top of the water and the creatures can still continue to live in the water underneath. Once that level of ice is on top, it actually insulates the water beneath so that it will not cool down quite as quickly and keep it from freezing. So to kind of sum things up here today, the structure of water, the fact that it is a polar molecule and the fact that it can dissolve things very well, and the fact that it exhibits hydrogen bonding makes a lot of these properties, these special properties of water possible, and it makes life possible on the earth. So we can thank a very wise creator that he created water the way that he did so that it is here for us to sustain life.